All right. Good evening. Welcome to the third problem-solving session of uh, Aeroengine gas turbine cycles course at NPTEL. Currently, no one has joined yet, so probably I will anyway start this video, and I'll be sharing the recording. So whoever is going to watch in YouTube, if you have any questions regarding this problem that I'm going to teach today, or solve today, you can always come back the next week and ask me if you have any doubts. So maybe what I will do is I will quickly go through what has been taught in week 3. Before that, let me check my recordings. Yeah. So I will quickly go through what has happened in week 3. So for the last 2 weeks, we studied about the general gas turbine engines. What are the different components we have? How do you thermodynamically analyze these components? Those were the things that we covered. But from week 3, what we are going to do is we are going to assemble these components and study as a whole, as an engine, how that engine will perform. How do you analyze a entire turbojet or turbofan engine? How do you go through each and every components, and how do you find its performance of that engine is what we are going to study uh, right from this week. So week 3 was turbojet engine, week 4 is going to be turbojet with afterburner, and week 5 we will start with turbofan engines. So this week we studied about turbojet engines. The so we turbojet is the simplest in construction. So for example, you will have inlet, compressor, combustors, turbine, and nozzle. So you will have these 1, 2, 3, 4, 5 components. And if you want to plot these thermodynamic processes in a TS graph, this is how an ideal uh, you know graph would look like. I mean, this is uh, so you have initially an isentropic compression, uh, which includes both inlet and the compressor, and and you will have like a constant pressure heat addition from 3 to 4, and from 4 to 5 you have turbine, where you will have uh, isentropic uh, it's an isentropic process in the turbine. And then from 5 to 9, again you have an expansion, isentropic expansion in the nozzle. And 9 to infinity, either the nozzle exit can uh, coincide with the pressure at the infinity. Typically this is not closed. There is no process as such, like we are not circulating the air again into the system. So it's like an open cycle, and this is how the ideal cycle would look like, and this is how an actual cycle would look like, because not all the process are isentropic process and a constant pressure process that happens in the turbine. You will have a real process which will be deviating from the ideal process. So if you say it's an isentropic process where this is a straight line, you will end up having a slight heating of the fluid, which would lead to a little bit higher temperature. Okay, so that goes to 2. And similarly, the compression, again, it will, because of the irreversibilities, which is going to include additional entropy. So that's why your entropy does not remain same. It increases a little bit, and because of that your temperature increases. And in the combustors, you are going to have a pressure loss. And similarly, in turbine and the nozzle, you are not going to have an isentropic expansion. You are going to have uh, uh, deviations from the isentropic. So 4 to 5 is that, and 5 to 6 is the.
Sir,
Yes, yes, Revati, yes.
there is disturbance in your call.
Uh, were you not able to hear properly?
No, I could hear, but a lot of other disturbances there.
Oh, okay. Um,
You have started much earlier, or just now you have started? I
so
was late, sorry.
no problem. Um, so maybe I will switch off the fan if that would help. Give me a minute. Do you still hear disturbances in my voice?
Yes, sir. Last week also it was like this, but
I see.
you there
Uh,
was some mic problem. You said no, it was fine last week.
okay. How about now? Were you able to have
Yeah,
any
now it's perfect.
Now it's okay, right? Okay.
Yeah.
Um, okay. So I have changed
Okay.
the mic now again. So let's see. Um, so anyway, so what I was doing is I was just going through, what we studied in this week's classes, and then I have like one problem to solve, which I will show it to you. Okay.
Okay.
So coming back, we have this TS diagram for actual cycles, actual processes, and this
Mm-hmm.
P6 and P9 will not exactly. Sometimes the exit pressure will match, so that we will take care. So at that time, P9 and P infinity will match. Sometimes it may not match, if especially when the nozzle is choked. So one of the problem that I'm going to solve, we will discuss about this. Um,
Okay.
and then we have like inlets, inlet compressor. We have already gone through what are the equations for this, for each and every components. So here, now we are going to see it as a whole. For example, initially we'll start with the inlet, and if we want to see after inlet what is the pressure rise, for example, so the whole exercise is to understand what is the pressure and temperature at each and every terminals of your engine. Okay. So here you need to know what is P02, P03, P04, P05, and P infinity or P9. Um, in addition, their temperatures also T02, T03, T04, T05, and uh, T9 and T infinity. So typically T infinity and P infinity we know, and based on the flight conditions, M infinity we know. So from there we can find P02 and T02 based on isentropic flow relations, and this could be altered if you have a efficiency, diffuser efficiency is there. So because again, as I said, it's just not, it won't be an isentropic process. Since it is not an isentropic process, you will end up having some diffuser efficiency in your pressure relation that you have here. And then similarly for a compressor, again we need to find what is the pressure ratio would be given. So we need to find what is the pressure at the exit of the compressor and temperature at the exit of the compressor. Then only we can calculate what is the fuel that we need to add to the add to reach TT4. So TT4 is also fixed uh, for these scenarios. So TT4 or T04 is the turbine entry temperature. Um, so to reach that temperature, what is the amount of fuel that we need to add? We will calculate from the combustor relations. So here you have like, so basically, mass and energy balance is what we are going to do. So this energy balance would give you F, um, and uh, and then in turbine we just match the power required by the compressor to the power uh, or work required by the compressor to the work extracted by the turbine. So based on that, we know that what is the amount of work we need to take from the fluid, and if we know the amount of work based on the thermodynamic relations, you can find the pressure and temperature at the exit of the turbine. So that's why we couple this work done by the compressor equal to work done by turbine. So at this point, we already know the work done to the compressor because we have already found pressure and temperature across the compressor. So only unknowns would be left would be of the turbine. And we know what is the inlet to the turbine. So based on this energy balance, here you can easily find uh, the T05, which is at the exit of the turbine. What is the temperature? Once you know temperature, you can directly find the pressure based on the isentropic relation. Uh, so here it's just rewritten in such a way that it is uh, so that you can write it in terms of terminal temperatures. That's why it looks complex. But since you already know terminal temperatures, you no need to rewrite. You can just use this simplified work equivalent, relation to find T05. So at the end of the day, we need to find T05 and T04, T03, T02, everything is known. Um, and for actual cycle, you will have additionally, turbine temperatures which you need to take into account. That's all. And finally, nozzle, we already solved one problem last week. We need to check whether the critical pressure is higher or lower than the exit pressure. Based on that, your nozzle velocity and temperature relations will change, whether based on whether the nozzle is choked or unchoked. So once you find V9, so which is what we want. Finally, we want V9, and we want what is the amount of F fuel that has been added, so that we can find what all the performance parameters such as thrust, TSFC, specific thrust, propulsive efficiency, overall efficiency, thermal efficiency, and all the other things. Okay. And then, the effect of pressure ratio, effect of turbine entry temperature, effect of m dot. We saw how these effects, all these things affects your, uh, thrust, TSFC. We saw that. And I'm not going to get into details, but if you have any doubts, we can always discuss. Um, and also, finally, we, you know, understood why we have to go from a single spool and to a dual spool engine. So because, um, sometimes because of pressure, uh, you want a very high pressure ratios, but increase in pressure ratio will also lead to an increase in temperature, and if increase in temperature, the velocity increases, and it could lead to, it would choke the flow, and it would lead to supersonic flow inside the compressor itself. And in those locations you will form shocks, and it will lead to a lot of losses, and it would be fatal to the blades. So that's why people did what they did is, that's why people actually went with single stage to multi-stage compressor. But if you want to further extend, you have to decouple two stages into two stages, lower and low pressure stage and high pressure stage, where low pressure will rotate at a lower speed, and high pressure will rotate at a different speed. So in that way you will decouple these into two different speeds, and hence you will have better control over the temperature, and you will have this is what you call it as a dual spool configuration. And then and then we see its advantages and where to use it based on your specific thrust and specific fuel consumptions, requirements. So if your aircrafts or if your engine lies in this upper portion of this graph, then you have to go with single spool. If it is in the lower portion of this graph, you have to go in a multi spool thing. So dual spool is nothing but you just divide, the compressor into two stages, and hence you have LP compressor and the HP compressor, and hence you will also have HP turbine and LP turbine, where HP turbine will drive the HP compressor, and LP turbine will drive the LP compressor. Okay, and only thing is the relations again you need to do two times. Calculation has to be done twice for each compressor and turbine. Otherwise, it's pretty straightforward calculation. And then we also see how these parameters affect different, uh, you know, temperatures, sorry, thrust, specific thrust, TSFC, and all the other things, efficiency. And yeah, so that is where we stopped. And we also, I think, professor must have solved one of the problem. I have a similar problem I'm going to solve today. And next week we will study about turbojet with afterburner. Okay, so if there are no questions, I will start today's material that I have. um, so this is a simple turbojet engine. I took this from a professor's presentation. So I just want to show each and every component's TS diagram. So initially there is an inlet, so that will give rise to this red color is the actual process, while the black is the ideal process. So from infinity to 2 there is a pressure rise because of inlet ramming effect, and from 2 to 3 because of compressor there is a pressure rise, which this part will be much higher than infinity to 2. Although this, I mean, don't take this graph as seriously. Infinity to 2 would be very small, and 2 to 3 would be very large. Okay. And 3 to 4 is the where you are adding heat or combustor is coming into picture, and 4 to 5 is the turbine, and 5 to 6 is a jet pipe or tailpipe. It's just a diffuser pipe. And from 6 to 9 you have nozzle, where you will have an isentropic expansion, or here it's not an isentropic process. Now for this problem, we just connected 6 to 9, where P09 and P infinity lies in the same uh, you know line, same isobaric line, but this may not be the case. So we will solve this problem. So today's problem, where you have a small turbojet engine with a compressor pressure ratio of 9, which means you have a uh, um, pressure is going to build up 9 times in the compressor, and the turbine inlet temperature is 1250 Kelvin. So this is the maximum temperature you can reach in your gas turbine engine. So which means this is T04. Okay, we are going to stick with the terminal numbers. For example, T04 is turbine entry, T05 is turbine exit, um, 03 is combustor inlet. So we are going to stick with that. um, the mass flow is 14 kilograms per second when the aircraft is flying at 280 meters per second. So this is going to be helpful in finding M infinity. And altitude is something like 7,000 meters. And at that altitude, you have temperature, pressure, and QR is the fuel, calorific value of the fuel. Calculate the propelling nozzle area required and the net thrust developed and the TSFC. So basically they are asking what is the performance parameters such as thrust and TSFC. In addition, we will also need to find out what is the nozzle area required for this. Okay. Um, and there has been given a lot of efficiency. So this is a real engine, and its isentropic efficiency at the intake, compressor, turbine, and nozzle is given. So these each and every components will have different efficiencies. The combustion chamber pressure loss is 8% of the compressor delivery pressure, which means whatever the pressure rise that compressor has given, 8% of that is going to be lost in the combustor. And the combustion chamber efficiency is 0.96. Okay. Um, so these are the given parameters from this thing, and efficiencies and losses are these. So in addition, I'm also ideally this also should be given, like the specific heat ratios and the specific heat of uh, the air and the flue gases or hot gases coming out of the combustion chamber. Here in this question, I didn't take it, so I'm assuming it here. So where air is 1.4, we know, and hot gases that is coming out of the combustion chamber, that is going to be in 1.3, the specific heat ratio. And CPC and CPH are specific heat, constant pressure specific heat. So we need to find these three parameters, A9, T, and TSFC. Okay. So this is how we are going to calculate. So we are going to go, step by step for each and every component. First is the inlet. We know its diffuser efficiency is 92%. So from T9, P9 and T9, ideally we will also have V9. If we take using that, and we know the inlet, the isentropic relations. Based on that, we will find P02 and T02. And once you find P02 and T02, we move forward with the compressor. And we will also take into account of 88% compressor efficiency. And the pressure ratio is one of the input to this calculation. So we will get from this, we will get P03 and T03. Okay. And once we know P03 and T03, we know we will have to calculate for the combustor. And for that, the inputs are both the calorific value of the fuel and also the turbine entry temperature. So that will help us getting F mass, fuel to air ratio. Okay, m dot fuel by m dot air. Or basically the amount of mass of fuel that you uh, give it give it to the combustor. And we will also need to know P04. So once we know these two, and also compare the work from compressor and turbine. We can find P05 and P05 and T05, and then it has to go through tailpipe or losses. Uh, but since the tailpipe does not have any losses, we are going to bypass that, and we will directly solve for nozzle, which has 95% efficiency, and from there we will find P9, T9, and V9. So once we have this P9, T9, and V9, we can directly find thrust and TSFC. So to find thrust and TSFC, you have to go through all these process of finding every terminal pressure and temperature. Okay. Uh, if there is any doubt, please stop me anytime. Don't worry about it. So we will proceed with the
Yes, sir.
yeah. So we will proceed with the calculations. So the first thing is we know P infinity, V infinity, and T infinity, which is like 41 kilopascals, 41.06 kilopascal. V infinity is like 280 meters per second, and T infinity is like 242.7 Kelvin. Okay, and we need to find P02 and T02. So before that, this requires M infinity, right? So for example, if I want to find T02, this is for an adiabatic process. Uh, Inlet still you can consider it to be adiabatic process, but it's just not isentropic process because entropy losses. That's why you have this isentropic efficiency of 92%. But still you can consider it as an adiabatic process, which means temperatures is there is no heat loss, and hence you can find temperature based on just this isentropic relation where you need M infinity as a input. So to find M infinity, you need to calculate from the V infinity. You also need to find the speed of sound at this condition P infinity and T infinity. So that is what we will first find. V M infinity is V infinity by speed of sound, which is gamma RT. So R is a gas constant for air. So we know it is 287, and this is V infinity is 280 meters per second, and gamma C is 1.4, and T infinity is 242.7. So if you perform this calculation, you can also do it parallelly if you have calculators and pen and paper with you. Uh, so it I think it would typically come around 0.89. Okay, and this is typical for a turbojet engines. So uh, the flight speed of turbojet engines sometimes goes through supersonic because of the some military aircrafts they go to supersonic. Uh, but any commercial engines typically they run subsonic, so they go till Mach zero point 0.8 or zero point 0.9 uh, maximum. So here it's a small turbojet engine, so it's just running at some altitude. So here the Mach number is around 0.897. This is the flight speed. So once you put this here, you can find out um, what will be the T02. T02 is nothing but the stagnation temperature. So since this is an adiabatic process, the stagnation temperature will not vary across the inlet. So that's what we are telling. Okay. Um, so if you substitute these numbers here, T infinity 242.7, gamma 1.4, and 0.987 square, you would end up getting 281.76 Kelvin as your stagnation temperature. So your static temperature is 242.7 and your stagnation temperature is 281.76 Kelvin. Now, um, now we also need to find out P02, and that is where the isentropic efficiency comes in. So P0, typically this eta D, if it is an isentropic process, this becomes 1. You will retrieve the isentropic relation for P02. But since this is not an isentropic process, this is a real engine, you have to include this second isentropic efficiency here. Uh, so if you include that, 41.06 is your P infinity, kilopascal. So please mind the units here. So you have to substitute into 10 power 3 here whenever your pressure is a. Typically we write in kilopascal, but when you substitute it, you have to substitute in pascals. And M infinity and gammas, if you substitute them, you would end up something like 66.57 kilopascal. So this is your stagnation pressure at the exit of the inlet. Okay. In addition, you can also find out what is P naught infinity, which means like what is the stagnation pressure at the inlet of the uh, diffuser, or which means um, yeah. So if you find out what is the stagnation pressure at the atmosphere, and if you compare that with this P02, that will be slightly higher than P02. So which means because of the diffuser, you are losing some pressure. So that's the uh, idea here. So now that we have achieved P02 and T02, we will proceed forward with the compressor. So since P02 is 66.57 kilopascal and T02 is 281.76, we know the pressure ratio is 9. So we can directly find P03. It's nothing but 9 times this 66.57 kilopascal. So that is what we will first find out, which will be something like 599.13 kilopascal. So which means around 5.9 bar. Okay. So around roughly 6 bar pressure. So inside the or 6 atmospheric pressure inside the at the exit of the compressor. Typically, this is how you will see, but in bigger engines you can go up to I guess 30 or even 40 pressure ratios, and in those places you can go till uh, you know somewhere near 10-20 bars also. But they will also fly at a very high altitude. So at that altitude, the static pressure itself is low. So for example, here itself we saw that P0 infinity is like 41. Uh, sorry, P infinity is like 41 kilopascal. Now, uh, in the ground, it's like 1 bar, right? So um, when you compare to the pressure at the ambience at that altitude, it would be a very high difference. Okay. Anyway, so we have this efficiency, compressor efficiency, which is like um, pressure ratio. Pi c is the pressure ratio here, which is P03 by P02. So pi c power gamma c minus 1 by gamma c. So this comes because of an uh, isentropic process, and this comes because of an actual process, right? So if you remember what is the isentropic efficiency of compressor, you will write it as change in enthalpy for an isentropic process by change in enthalpy for an actual process. So change in enthalpy for an isentropic process will be simply a function of just the pressure ratio. But change in enthalpy of actual process, we don't know that it should be a function of efficiency. So that's why so now our idea is to find T03, where tau c is 303 by T02. So you will rearrange it. T03 by T02 is nothing but 1 plus pi c gamma c minus 1 by gamma c minus 1 divided by eta c. Since we know compressor efficiency, you just substitute these values 9, and then if you do this calculation, you will end up having a temperature ratio of 1.9925. Please cross check this results. Um, Hopefully I did all the arithmetics right. Okay. So now we know T02 is 281.76 Kelvin. So if you substitute that with 1.9925, I mean, if you multiply that with 1.9925, you will end up having 561.42 Kelvin. So that is the temperature rise you will get across the compressor. And you will also see I mean, here we are talking about just the stagnation temperature. This is not an static temperature that you will feel there. This is a stagnation temperature. Okay. So now this is the stagnation temperature at the end of compressor. Now, since we found all the terminal temperatures at the end of compressor, we will proceed forward with the combustors. So from the compressor, we have P03 to be 599.13 kilopascal and T03 to be 561.42 Kelvin. We know the combustor efficiency is 96%, and this 561.42 Kelvin has to be heated up to 1250 Kelvin. So if you want your air to get heated up to 1250 Kelvin, you have to add some fuel, do some combustion inside. What is that amount of fuel that you're going to add is what we are calculating in this calculation. Okay. So first thing we need to find out is F. Okay. So yeah, maybe we will find out it after we find the pressure losses, because that is easy to do it, because we already know uh, there is a 8% of the pressure loss that is going to happen from P03 to P02. So if that is the case, then 599.13 times 0.92 should give you what is P02. So so this pressure loss P03 minus P04 is nothing but 8% of P03. So if I rearrange it, it is going to be simply 551.2 kilopascal. So we know the pressure. Now, as I said, we need to find out what is the amount of fuel that we have to add to raise this temperature from 561 to 1250. So for that, we will do energy balance, where the inlet is has only M infinity is the mass flow rate of air, and CPC T03. So CPT is the enthalpy which is which the air is entering with, and what I'm adding is a fuel M dot F times some burner efficiency is there, so that we need to include times the calorific value of the fuel. So this is the total energy content I'm adding as a fuel. This is the total energy content that is entering as air. Okay. And finally, this is the total energy content that is going to leave from the combustor, which is going to be M infinity plus MF times CPH. So if you have to be a little careful here. Whatever enters is CPC, and whatever is going to leave is going to be a hot flue gas. It's no more air. Okay. No, you cannot use same CPC here. So this will be CPH, and it is going to leave at 1250 Kelvin. So in this relation, only thing we don't know is M dot F, because we know QR, eta B, T03 we know, T04 we know what is the temperature we are going to rise it up to. So only thing we don't know is MF. So I'm just going to rearrange this relation in such a way I can directly get F in terms of M infinity. So uh, if I do that rearrangement, it is going to be something like this relation. So uh, what I'm trying to say is you no need to remember this relation. You just need to know energy balance. What is coming in, what I'm whatever is entering. One is air is entering, one another is fuel is entering, and what is leaving. So you just need to calculate that. And once you see, if you can devise this formula, you can simply rearrange to get F. So basically, you no need to remember whether T02, T04 should come or T03 should come, which should come first. You no need to remember all those things in this relation. Okay. Um, anyway, we have rearranged it from this. And then if you substitute these numbers, CPH is 1157 and CPC is 1005. T04 is 1250 and T03 is 561.42 Kelvin. And similarly 96, this and this, if you substitute it, you will end up having fuel to air ratio to be 0.0 0221. Okay. All right. So now we already know pressure and temperature at the exit of the combustor. Temperature is 1250 Kelvin, and in addition we also know fuel to air ratio. Okay. So which means whatever the component after combustor is not going to have only M dot infinity, it is also going to additionally have M dot infinity. In addition to M dot infinity, it's going to have M dot F. Okay. So the future calculations should also include M dot F. All right. So this is the turbine. And for turbine, we already know T04 and P04. That is what the air and air fuel mixture that is entering. I mean, it's no more fuel. Fuel has been combusted. So hot flue gas that is entering the turbine. And it is going to leave at P05 and T05. But this is going to generate some work. And that work done also you need to find out. And P05 and T05 also you need to find out. Uh, So to find out the work done, first we will do energy balance. Again, the same energy balance. So the amount of the amount of work done to the fluid by the turbine, okay, sorry, our amount of work done by the fluid to the turbine is nothing but equal to some efficiency. This lambda is the efficiency, some efficiency times the amount of work uh, given to the compressor. So not all the work gained by the turbine is given to the compressor because of some mechanical efficiency, wear and tear with the spool, and sometimes you will also have some gearboxes. uh, you will study about that in geared turbofan engines. So those things will have additional mechanical efficiency. So you will have bearings which supports these shafts. So all these things could have additional wear and tear, which could lead to a mechanical efficiency. Okay, in this problem, I am going to assume there is no mechanical efficiency. So here in this side you have the left hand side is like m infinity 1 plus f c p h t04 minus t05, which is basically the energy of air entering minus the energy of air leaving is equal to m dot infinity into cpc t03 minus t02. So this is basically a total enthalpy change across the compressor. So now in this relation, we already know f, m infinity, cph, t04 is known. Only unknown is t05. Okay, so you can directly use this to find t05. So that's what I did. I just rearranged it in a familiar way, which you can either do this or you just directly substitute the numbers here and directly find out t05. It's totally fine. You can either find it like t05 by t04 or you can directly find it. So there's no problem in that. And if you substitute these values here, you will end up having T05 to be 0.8099 times 1250. And if you substitute this, you will end up having 1012.33 Kelvin. So your temperature of the hot gases is reduced from 1250 to 1000 kelvins. So that is the amount of energy that has been extracted by the turbine, which means that is the amount of energy compressor needs it. Okay, so that's it. If you have a mechanical efficiency, let's say if this efficiency is no more 100%, if it is 90%, so this temperature would be even lower. Okay, because it needs to extract more energy to give lesser energy to the compressor. So this one will be even more. Okay, so we already found T05 now. We need to just find P05. So how do we find P05? We have studied this, right? So the turbine isentropic efficiency is there. From the since we know the isentropic efficiency is 92% for the turbine. Uh, from that relation, you can find P05 by T05 to be. So that is how you get this relation. So I'm not deriving it again, but you can check the notes. We studied this in week 2. So we will just substitute these numbers here. T04 is known, T05 is known. Everything is known in this except T05. So if you substitute these numbers, you would end up having 0.367 times 551.2, which would be like 200 kilopascal. So the pressure has reduced from 551 to 200 kilopascal. So the next component is tailpipe or jet pipe, whatever you call it. But here it does not have any losses. So P05 and T05, or P05 and P06 and T05 and T06 is going to be same. 202.29 kilopascal and 1012.33 Kelvin. Okay. Now the next component, final component here is nozzle, and nozzle has some efficiency. So before we find P9, T9 or V9, we need to know whether the nozzle is choked or not. So to understand that, what we will do, we typically use the critical pressure ratio. So that's the choking condition that we will find out. So first is critical pressure. So which is P06 by P critical is going to follow this relation, and the nozzle efficiency is 0.95 percentage. So you substitute these numbers, you will end up having the pressure ratio to be 0.89, 1.896. So you can find the critical pressure using this. It is going to be 106.69 kilopascal. So if your exit pressure is or ambient pressure P infinity is greater than P critical, then it will be nozzle will be not choked. If the P critical is greater than ambient pressure, then the nozzle will be choked. So for in this case, at 7,000 meters height at uh, and in that height, the P infinity was only 41 kilopascal. So which means the critical pressure is higher, which means the nozzle is choked. And if the nozzle is choked, then at the exit of the nozzle, the velocity of the or the Mach number of the hot flue gas that is exiting the nozzle is going to be 1. Okay. And that is the isentropic relation that we are going to use to find out what is V infinity. So this is P9. So we found out P9. P9 is going to be same as critical pressure for this case because the nozzle is choked. And now we will have to find T9. T9 is going to be T naught. It's going to be gamma H plus 1 by 2. So if you remember, um, T naught by T is nothing but 1 plus gamma minus 1 by 2 m square, right? In that m square, if you substitute m to be 1, you will end up having this relation, gamma plus 1 by 2. So 1 minus gamma, uh, 1 plus gamma minus 1 by 2. If you rearrange, it becomes gamma plus 1 by 2. And this gamma H is the hot flue gases. It's not air. So you will have to substitute 1.3 and this will become 1.15. And hence you can find T9 to be 880.3 Kelvin. And since you already know T9 and you know gamma H, you can basically find out the velocity. So the only problem here is this R, the gas constant of air. So I took gas constant of air. So sometimes in a problem they will give the gas constant of flue gases, hot flue gases also. So at that time you cannot use this 287. You have to use that gas constant. Okay, because the properties have changed once it has gone through the combustor. All right. So
Sir,
yeah.
why at the exit we are taking the static properties, not the total properties? Everywhere else we were taking T0
Hmm, hmm, hmm.
stagnation property. At
Right.
the exit alone, why we are taking static one?
Because we need to find V infinity. So velocity depends on static temperature. Right. So that's why we need static temperature to find V infinity. The stagnation is not going to. So imagine, see, this is a nozzle, right? So it is in an ideal scenario, it's going to go through isentropic expansion. During an isentropic
Yes.
expansion, the stagnation properties will never change. But since this is not
Okay.
a isentropic process, but still it's an adiabatic process. Nozzle you can consider it as an adiabatic process. So the stagnation temperature, for example, T06 and T09 is going to remain same. Okay, but
Okay.
P09 would be different because it has some isentropic efficiency. But finding out P09 is of no use to us. It's not going to help in any way for our calculations. You can find out and keep, but it is of no use. Only thing we need is velocity at the exit of the nozzle at the end of the day. And also we need static pressure at the exit of the nozzle because your thrust equation has both V9 and P9. It does not have
Okay.
P09. So that's why we don't calculate it. But one can actually calculate and see this will be the stagnation pressure that you can always do. But since it is not
Okay.
useful for us, we are not doing it.
Okay. So the previous stages we are taking stagnation properties.
Right.
With that only we are calculating the static properties. That
Correct.
will not make any change in our calculation
Exactly.
because those are stagnation.
Right. Yeah, it will not. So,
Okay.
uh,
Okay.
and see, one more thing is we don't really need to know, static properties, before nozzle. So there is no point in understanding, see, compressor is
What
going
is
to
that?
change the
Okay.
stagnation properties. That is for sure. Turbine again is going to change the stagnation properties. One can actually find what is the static properties at the exit of compressor, turbine, every station you can actually find out because you already know the efficiency, you know the isentropic relation,
Yes.
you can find out, but it is unnecessary. It is going to be no use to us, right? So we are
Okay.
just finding out whatever the properties that are useful. There is no harm in doing either way.
Okay. Thank
Okay,
you.
all right. So so once you substitute this in this relation, since its Mach number is 1, the velocity is going to be same as sonic speed, which is gamma RT, and hence you will have 573.1 meters per second. So that will be your exit velocity and also temperature. Again, here temperature is not directly affecting thrust, but we need that to find out V9. So that's why we are finding this also. Okay. So once you do this, the first thing that we need to find out is the nozzle area ratio. The nozzle the nozzle area is nothing but you can use m dot relation. M dot is equal to rho av. Here rho we know. How do we know? We know ideal gas P9 by R T9. Okay, we can find rho 9. We also know V9. We also know m dot through the nozzle, which is nothing but your m dot infinity plus m dot f, mass of air and mass of the fuel. So
Sir,
yes,
sir, excuse me, sorry to interrupt. Actually, I joined a little late. My name is Robbins.
no problem.
Sir, I guess your this problem is about one of the problems that we have to find the. I mean, from a list of assignment number 3, there are 10 questions based on one single calculation. Is that the one that you're talking about?
Correct. Yes, yes. This is exactly what I'm
Oh,
talking
oh,
about. So, for example,
all
we
right.
started with this turbojet engine. It was given.
Yeah.
So we have been given. What is the pressure ratios and mass flow rate, and also the efficiencies, and we have to find out thrust, PSFC, and the area, nozzle area at the exit.
Oh,
So
yeah.
to do that, we have
Oh,
to go through each and every components,
sure, sir.
and we
I'll,
have
I'll
to
watch
find out.
it. I'll watch it later. I don't want to waste your time.
Yeah,
So,
yeah, yeah,
sir,
sure.
I was a little bit struggling on that whether the nozzle is chalked or unchocked, because when I did the calculations for the assignment, I got around 39 point, and the static pressure was given around
Okay,
40.
ha ha ha. So this
So
this
I assume
problem, no, no, no.
I answered. Sorry. Yeah.
This problem is not the same as your assignment problem. So we don't want to,
All right. Then
we don't
it's
want to show you
then
the,
it's fine.
yeah, yeah. So this is a
Yes, sure.
different
Yeah.
problem,
All right. Sir.
but it's a
Sure.
similar
Then it's
problem
fine.
what you are going to solve in your assignments. So I'm not
Okay.
going
All
to
right.
spoil, your
No, no,
uh,
no, sir. Actually,
your
that
answers.
was a mental math. Actually,
No, no,
it
no,
took a
no.
lot of effort, but still I couldn't find the answer. That's fine. Okay.
So yeah, I mean you this don't worry about this answers. So this is a different problem, but it is a
Yeah.
similar to whatever you will be solving in assignment 3. So that is the thing. But whatever your answer
Sure.
is, you be confident on that.
Yeah.
If you do your calculations right, that should be the right answer. Okay.
Sure, sir. In my problem, sir, I got the nozzle as chalked. Then, yeah.
Okay.
Sorry, unchalked. That's
Okay.
right. Okay.
It could be.
All
Yeah.
right, sir. Please
We
carry
don't know
on.
that. Yeah.
I'll listen to you.
Yeah. Yeah.
Oh, thank
Sure.
you.
No problem.
Oh,
Anyway, so basically what I'm saying is density we know, V9 we know, and M dot we know. So we just need to rearrange and we get A9. So you can rearrange like this, you can follow this, or you can directly find density and substitute in this relation to find A9. Okay. So the A9 comes out to be 0.059 meter square. So which means for these conditions, let's say you have to design your gas turbine engine for a single design point. Okay. So uh, if you are designing for this point, let's say it could be any engine, it could be for any application. Let's say if it is flying at this altitude, and this is the ambient pressure and temperature, and if it is moving at 280 meters per second, I want to typically move that engine at 280 meters per second. It could be attached with uh, and small aircraft, for example. Then, and most of the time I will be operating that aircraft at 280 meters per second. So that is my mission statement. And if that is the case, what should be my ideal design nozzle area? If you ask me that, then that would be 0.059 meters square. So this is one of the design parameter that you have to include it. Okay. And then since we know A9, we can find the thrust. So here we already know P9. We've just found out from nozzle. It is same as critical pressure. And we have V9 and we have V infinity. We have F we found out. So you just substitute everything here. You will end up having 8152 newtons or 8.1 kilonewtons. And your TSFC is going to be simply m dot F by T. which is F times m infinity by this thrust. And if you substitute that, it is going to be 3.795 into 10 power minus 5 kilograms per second per Newton. Kilograms per second of fuel per Newton. But typically people also write it in terms of kilograms per hour per Newton. That would be something like 0.137 kilograms per hour per Newton. Okay. All right. And then finally, efficiencies also we need to find out. I mean, in the question it was not asked, but I thought I will show you how to find out efficiencies. So since we know thrust and V infinity, we can directly substitute this in the propulsive efficiency, the first variant where we do not exceed 100%. So if you substitute that, the propulsive efficiency comes out to be something like 56%. Okay. And similarly, the thermal efficiency is coming out to be slightly lower, which is around 30.61 percentage. So which means overall efficiency is going to be even lower. That will be something around 17.16 percentage. So this is the typical efficiencies that current aircrafts are operating at. For example, if you go to turbofan engines, this propulsive efficiency will be slightly higher. It goes through maximum 80% for state of the art turbofan engines, and the thermal efficiencies goes to maximum 40 to 50%. So which means overall efficiency is still around 40 to 50%. So that is the state of art currently in the gas turbine community. Okay. To conclude, this is I have modified this TS graph. So you see that since the nozzle is choked in this problem, you have your P9 does not coincide with P infinity, so it will be at a higher level. So if you want to draw a TS diagram for this engine for these conditions, it should be something like this. It should not come down to P infinity. Okay. So that is the difference. If the nozzle is unchoked, then it will come down to P infinity. Since it is choked, it will come up. Okay. All right. So that is what I have today. If you have any questions, please feel free to ask. So the next week, what we will do is we will do the same turbojet engine. We will keep everything same, but only thing is in week 4 you will be introduced to afterburners. In addition to turbine, after turbine you will also have an afterburner section where you will additionally add fuel and increase the heat or increase the temperature of the gases that is coming out. And that is going to affect your thrust and other things. Okay, so when the afterburner is included for this same engine, how is your thrust, TSFC, and the efficiencies are going to vary? We will see that, and we will compare our today's problems solution and also the next week's solution together to understand what is the effect of afterburner. Okay, so you will learn more about afterburner in week 4.
Sir, I don't know whether this covers in the topic, but just for my curiosity, I work in aviation, so
Okay.
yeah, normally I think this topic covers only two-spool engines because and for Rolls-Royce and all, they use the three-spool, which it have got an IP
Right.
intermediate pressure also.
Right.
So I hope in that case the station numbers will also change. The engine station numbers there will be instead of 02 to 03, that is one set of compressor and
Right. So yes,
yeah.
this will change. In fact, we do have I think week 6 or week 7 deals with 3-spool engines, and also
Yes.
week 6 I think gear
That's
turbofan you will have. Week 7
yeah.
you will have 3-spool engines. You will also go through
All right.
ultra high bypass ratio turbofan engines.
Yes,
There we will
that's
keep
one
on
of the
updating the station numbers.
yes, sir.
Yeah.
I think all this what you have discussed today is about low bypass or medium bypass engines.
No,
I
this is not turbofan engine at all. There is no bypass coming into picture here.
oh, this is
This is
turbojet.
just a turbojet,
Turbojet.
simple turbojet engine.
Oh,
There is no bypass flow. Okay, we didn't
all right,
enter
sir.
that. We didn't enter that scenario with bypass
No,
ratio.
sir. Yeah.
That will come in week 5.
Oh.
Week 5 you will be introduced to turbofan engines. That's where the bypass
Okay.
ratio comes into picture.
No. That's why the next session is about afterburners because since we are talking about
Turbojet. So we will complete that with afterburner. Again, for turbofan,
Yeah.
again we will revisit afterburner again. Okay. For
Okay.
turbofan also you can have afterburner. For example, uh, previously, in World War II and after that, people were typically using turbojet engines for military aircrafts. Nowadays, they have advanced it and they are using low bypass turbofan engines. And with low bypass
Okay.
turbofan engines, they are also using afterburners. So it
Okay.
is also important to study about afterburners and you know in the turbofan engines. Sometimes you might think that so turbofan engines are typically designed for not for a supersonic speed, and hence you might be thinking that turbofan engines may not be useful for military aircrafts, but to typically turbofan engines improve the efficiency, and that's why they are currently used in military aircrafts where you can go at supersonic speeds too. So yeah, so there are some things that you need to take care when you go from turbojet to turbofan, and there should be some logical step behind why to move from a turbojet to turbofan. So all those things we will study in detail, in coming weeks. You will understand that more if you don't understand it now. Don't worry about it.
Sure, sir. Sure. Thank you.
All right. Uh, if there are no more questions, then maybe I will meet you next week. Anyway, I will stay back till 5 o'clock in this call. If you have any questions, you can ask. If not, thanks for joining, and we will meet next week. Uh,
All right, sir. Thank you.
Thank
Yeah,
you.
just to introduce myself. Yeah, I'm in the middle of driving, so yeah, we are working. So see you next week, sir. Bye.
Yeah, yeah, sure, sure. Bye.
Sure.
Thank you, sir.
Thank you, Revali. Thanks for joining.